Okay, these notes are over describing and summarizing quantitative variables. So here we're going to start discussing how to describe a distribution. So we're going to be using the acronym SOX. And what I'm going to do is I'm actually going to add another C in here. And what SOX helps us remember is how to describe a distribution. So S stands for shape, O for outliers, C for center, the other C for context, and then lastly the S for spread. Okay. First, looking at shape, we use these words to describe the shape of a distribution when it is graphed. Typically, you pick one word from this top portion, and then you pick one word from this bottom portion here. So unimodal, what that means is that the graph has one hump. Okay. Bimodal means that it has two humps. Okay. And uniform means that they're about all the same height. And again, emphasis on about. Doesn't mean they have to be the same height, but they are about the same height. Next, we're going to look at symmetric. Symmetric means if you were to take these and divide them in half, they would be the same on both sides. So here's one example, and then another example could be the bimodal. Okay. Then we have left skew and right skew. So for left skew, okay, you'll notice that all your data is on the right side. So think opposite. Okay. And then for right skew, all of your data will be on the left side. And this little portion on each of the skewness is called tails. And the tail is where the least amount of data is. Okay. So in class, I had you guys take a minute, break into your groups, and try to do each of these scenarios. So first was to draw a symmetric bimodal and then a unimodal right skewed. Okay. If you want to try these on your own and then kind of compare with everybody in class, that would be great. The next one is outlier. So an outlier is a piece of data that falls outside the overall pattern of the distribution. So it's data outside the pattern of the distribution. Okay, so when we're looking at outliers, the reason why we find these outliers is we want to see if getting rid of these pieces of data will influence our overall distribution. Will it change the mean? Will it change the median? What will this do? And then also, why did that outlier happen? Okay. We'll come back to outliers towards the end of this video. Next is the center. So for center, there are three measures, and that is mean, median, and mode. Okay, and then remember, mean is the average, median is the middle number, and mode is the number that populates the most. I'm going to start off right here and say mode is useless. We are never going to use mode when describing the center. It will always be mean or median. Okay. Then what we did in class is we collected data here, and this data was how many siblings does everyone have? Okay. I want you to copy down the data that matches with your class, and what we did with that data is that we found the mean. And remember, mean just means we're taking the average. But here we have a formal definition of mean, and that is going to be x bar is equal to the summation of xi over n. And these symbols, so for example, the X bar just means mean of a sample. X sub I means an individual observation. So for example, if we go back to the siblings example, when I asked everybody how many siblings they had, each person in the class is categorized as X sub I. So like X sub 1, X sub 2, so on and so forth. N is the number of observations, or the total that we collected. And then capital sigma means to take the sum. Okay, so comparing to all three courses, a lot of you guys got a mean number of about 1 to 2 siblings. So I'm just going to use the number 2.45, and I'm going to label that siblings because siblings is my unit. It is very, very important not to forget that unit, okay? Because if you're showing this data to somebody, 2.45 doesn't mean anything. 2.45 GPA, 2.45 dogs. Like, what is it talking about? And here we're talking about siblings, okay? So now we're going to look at another example. In this example, we have 7 exams and all of their scores. Okay. Notice that one of the scores is 0. Well, this is clearly an outlier, but what would be some reasons that this person got a 0? Okay. One reason you guys said is that they're absent. Okay. And another reason you said is that they just failed the exam. But I'm going to tell you, failing an exam with a 0% is just as hard as passing an exam with a 100% because they had to know in some way or another which values or which answer choices not to pick. So the most common thing that happened here is that the student was absent. Okay? Well, if they're absent, that means that's not really their true score. So we could get rid of it since it is an outlier. However, let's calculate what the mean would be with the outlier and then without the outlier. And when you do this on Desmos, okay? You add them all up and then divide by the total number. The first one with the outlier is 78.3, and the next one without the outlier, so this is with and this is without, is 91.3. Notice that when we remove that outlier, our average goes up. But with that outlier, our average goes down. So it says, what is the outlier doing to the mean? Well, it's bringing the mean down. And because of this, we call mean to be non-resistant. And I used the example in class, the difference between non-resistant and resistant is think of non-resistant as the follower. They have low self-esteem. They are susceptible to peer pressure, all of the above. Versus resistant, they're the leader. They have the confidence. Nothing is going to change their path, their personality, their presence because they are the leader. So we have resistant and non-resistant. So again, non-resistant is strongly influenced by extreme values. Well, we say the mean is non-resistant because notice how when we found the mean with and without the outlier, we got a drastic change in our data. Okay. On the other end, resistant, a resistant means of measure would be the median. Okay, and that is, if you recall, the median or the middle value. And we know that the center using the median is not as affected by extreme values like outliers, just like the mean is. Okay, so continue using the example of the siblings. Of course, I would want you guys to write down the data that goes with your class. What I'm going to do is I am going to just write down some random data to just show you to find the mean and the median, and we're going to compare that with also the test scores in the other example. So if I'm writing this down, actually, let me get rid of that. Okay, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, again, this is just some random data. Okay, if I was to find the mean or the average, I would get 2.45. But if I was to find the median, and remember we do that by crossing out each of them until we get to the center. I would get 2. Okay, notice that 2.45 and 2 are very similar. They're not exact, but they're close to each other. Now, if I were to bring down the mean that I found in the test scores and then find the median, notice how the median relates very closely to what the mean looks like without the outlier. Because remember, the mean without the outlier was 91.3, and the median, even though the outlier is there, is still around 90, which makes it a better descriptor for the center versus the mean, because the difference between the mean and the median are very drastic. They are very different. Okay. Next, what I had you guys do in class as a little activity is take this data, and you could have done a histogram, a dot plot, any of those two things that I showed you how to do on Desmos, and then you are finding the mean, median, and mode, and then listing the shape. Okay, so you're describing, okay, was this symmetric, was this right skewed, was it left skewed? Okay. So to summarize what we just talked about with the center, with the mean, median, and mode, the important thing to know here is that if we're dealing with unimodal or symmetric, okay, so here's my symmetric unimodal, one hump, okay, and here is my center, that no matter if we use the mean or the median, we're going to get similar values. So mean, similar to median. And I'm just going to shorthand median to MED. And then if I was to look at left skew data, and this was my center, okay, you would find that the mean is actually going to be a lower number than the median. Okay. And then for right skew, okay, we'll notice here that it is the opposite. So the median is going to be less or smaller than the mean. Okay. And then the last part of our acronym SOX is spread. And when we're talking about spread, we're talking about range, standard deviation, and then from here on forward, I'm not going to write standard deviation. I'm going to write just SD to shorthand it, and then IQR. Okay. We remember how to find the range by taking the maximum value minus the minimum value, and that gives us the range. Notice that when we find range, it's just a number and not an interval. Now let's look at standard deviation. Standard deviation is the average deviation from the mean. Okay, and we're going to do a little activity here together to show you where the standard deviation formula is coming from and maybe give you a little better understanding of what it is. So here in this example, we have a group of elementary school students, and each of these values is how many pets that they had. So taking all these values, I would add them up and divide them by the total, which is n equal to 9, and I would get the mean of 5. Okay. Remember, all of these observations can be written as x sub I. So this would be x sub 1, x sub 2, x sub 3, all the way to x sub 9 for our n equals 9 value. Well, for the deviations, we are seeing how far away these numbers are from the mean of 5. And so if the number is smaller than the mean, then it's going to be in the negative direction. It's going to be to the left of the mean. Versus if the number is greater than the mean, when we calculate this, it's going to be positive because it's to the right of the mean. Okay? So what we would do here, looking at each of these, is we would say 1 is 4 away from 5 on the left side, so negative 4. 3 is 2 away from 5 on the left side, so on and so forth. And I'm just going to go ahead and fill the rest in. And notice when I get to 5, 5 is exactly the mean, which means there's no deviations from it on the left or the right. So ultimately what we just did is we took our observation value and we subtracted the mean. 1 minus 5 is negative 4. 4 minus 5 is negative 1. 9 minus 5 is 4. Now we are going to find the square deviations by squaring each of these values. So 16, 4, 1, 0, 4, 9, and 16. So again, all we did was we take x sub I minus the mean and square it. Okay. Now what we're going to do is we're going to find the average squared deviation. So these are the squared deviation. In order to find the average of these numbers, I'm going to add them up and divide them by the total. The only thing that's going to differ here is that instead of just dividing by the total, I'm going to divide by the total minus 1. And what that means is something involving calculus. So if you're in my calculus class, great, we'll go over that later. In a different unit than we are working on right now. And if you're not in my calculus class, don't worry about it. Just trust that I'm correct. Okay? So the formula for this would be the summation of x sub I minus x bar squared over n minus 1. So if I was to add up all these square deviations, I would get 52. 52 over 9 minus 1 is 52 divided by 8, which is 6.5. Okay, the value 6.5 that we just found is called the variance, and the variance is the average square deviation away from the mean. Okay. However, when we find the variance, the units are now squared pets, because remember originally we were asking each of these kids how many pets they have. So pets was the original unit, but when we squared everything, we end up squaring the units. So in order to undo that, we're going to take the variance and take the square root of it, so the square root of 6.5, and we get what is called the standard deviation of 2.55 pets. So referring back to what we just did for variance, I'm going to rewrite the variance formula with the correct symbols. So this is s sub x squared is equal to the summation of x sub I minus x bar squared over n minus 1, where s sub x squared is variance, x bar is mean, x sub I is individual observations, n is the total, capital sigma is the sum, and s sub x represents standard deviation. So ultimately what we're doing is we are taking the square root of variance to find the standard deviation formula. So standard deviation is equal to the square root of variance, which gives us the square root of the summation as x sub I minus x bar squared over n minus 1. And again, if we were to interpret the standard deviation in context of the problem, this would mean the number of pets typically varies from the mean by 2.55 pets. So again, what that means is we know here this is our average. Our average is 5 pets, okay? That means anybody in that one class where we took the data from can have the mean plus 2.5, so they could have 7.55 pets. So that's in the positive direction. Or they could have 5 minus 2.55 pets, which is 2.45 pets. So that means our data could deviate from 2.45 pets to 7.55 pets, around the average of 5 pets. And again, we'll talk about this a little bit more when we introduce the empirical rule and we start talking about normal distribution. The big thing here, extremely important, is that when you are interpreting the standard deviation, you use these words. Typically varies from the mean by. You will get it marked wrong if you do not use those exact words. Okay, so continuing on with standard deviation, when we are using standard deviation for spread, that means our chosen measure of the center has to be the mean. So when we choose mean, we choose standard deviation, which means if I choose median, I am not choosing standard deviation. Okay, and we'll talk about in just a minute what you would be using if using the median. But first, some properties of standard deviation. We know that it's always positive. Well, that makes sense because variance, we had to square everything. So once we square everything, it's automatically positive. And then when we take the square root of a positive number, we're going to get a positive value. Also, standard deviation is 0 when the observation, so x sub I, is equal to the mean, x bar. We saw that in the example of the pets when our mean or our average pets was 5 and one of the students had 5 pets, so it canceled out to 0. Standard deviation has the same units as the variable. So since our original variable was talking about pets, standard deviation should also have the unit pets. Okay. The standard deviation is non-resistant, which again means that outliers or other extreme values will make it extremely large. And that makes sense because remember, mean was non-resistant. And if mean is non-resistant and we have to use standard deviation with mean, well, that means standard deviation is going to be non-resistant. Okay. And then lastly, the greater the standard deviation, the greater the variation of the distribution. And with that being true, okay, so the bigger the standard deviation, the further away we are from the mean. We do not want that. So just keep that in mind. We want our standard deviation to be as small as possible because we want to look at all the data values closest to the mean. Okay, if we get larger and larger and larger, it kind of defeats the purpose of looking at this data because we now are no longer getting a very accurate reading or interpretation of it. Okay, next we're going to talk about IQR. IQR is the interquartile range. It uses percentages to describe this, percentiles to describe the spread. Okay. We already talked about what percentiles are when we talked about the cumulative relative frequency graphs, or OGIFs. Okay. And before we continue on, we're going to go ahead and give a name to each of the most common percentiles. So the 0 percentile would be the minimum, and the 100 percentile would be the maximum. Which means in between these two, the minimum and the maximum, would be the median, and that is the 50th percentile. So when we are talking about IQR is related solely to the median when using that center measure value. And now looking at the 25th and 75th percentile, what this stands for is the first quartile and the third quartile, which we label as Q1, Q3. All five of these values here are called the 5-number summary. When we are using the 5-number summary, if you are asked to plot that data, you will always be asked to plot a box plot. Okay. So in order to create a box plot, you need to find the 5-number summary. So in this example, we have data from a previous class of how many hours of sleep these students got before the first day of school. And look at this poor guy right here. Why did he only get 2 hours of sleep? And then we got all the way up where it looks like the majority is 7 hours of sleep, and then the maximum right here at 8.5 hours of sleep. Okay, so what I'm going to do first is I'm going to identify the minimum, which I said was 2, and the maximum, which I said was 8.5. And then in order to find the median, I need to make sure my values are in order numerically, so from smallest to largest, then cross off each side until I end up with one number left in the center. And as I get closer to doing that, you'll notice that I end up with 2 values. Okay, since those values are the same number, I know that my median is 7. But let's say they were different numbers. Okay, if they were different numbers, then I would take the average of them. So add them up and divide them by 2. Well, since this is my median here, what I'm going to do now is I'm going to find my Q1 and Q3 by looking at all of these values here. Okay. And then find my Q3 by looking at all these values here. So the Q1, or the first quartile, is just me finding the median of this little section that I highlighted in blue. I'm trying to color code these as much as possible so it's easy for you to follow along. So in doing that, I'm going to cross them off until I get to the center value. And notice I end with 6 in quartile 1. And 8 in quartile 3. So I'm just finding the median within the median. Then I need to find the IQR. And remember, IQR is related to range, and we know that range is maximum minus minimum, but we're only looking at the interquartiles. So that is Q3 minus Q1. But just like the range, our IQR value will just be a single number. So if we're calculating that for this scenario here, Q3 minus Q1 means we have 8 minus 6, which gives us 2 hours, because we never forget our units when we're doing a problem. So 2 hours would be the IQR between the students who got sleep before the first day of school. Now that we have our 5-number summary, we're going to create a box plot to show that distribution in a more visual manner. In order to do that, I'm first going to go ahead and label this axis at the bottom, and I'm going to start at 1 and end at 9 since my minimum was 2 and my maximum was 8.5. So I want to make sure I encompass all of those values. Okay, and then I can't forget to title this, so this is hours of sleep. And then I'm going to label all the points before I draw my box. So my minimum was at 2. My maximum was at 8.5. My median was at 7. My Q1 was at 6. And my Q3 was at 8. Now I connect those lines that I did, and I just created a box for my box plot. And then I'm going to connect the end dots to my box plot, and these lines right here are called whiskers. So here is my box plot. Okay. However, let's say we're using the 5-number summary and we need to figure out if our box plot has an outlier. In order to do that, we would be using the outlier test. For the outlier test, you need to first label the 5-number summary, find the IQR, and then compute the lower and upper bound formulas. So for our example above, is there an outlier? So first we would do our 5-number summary. So minimum was 2, maximum 8.5, median 7, Q1 6, and Q3 8. Then we would do our IQR, so that's Q3 minus Q1 equals 8 minus 6, which is 2. And then I would do my lower boundary, or LB, which is Q1 minus 1.5 IQR, which gives me 6 minus 1.5 times 2, which is 3. And then my upper boundary, or UB, which is Q3 plus 1.5 IQR, which is going to be 8 minus 1.5 times 2, or sorry, plus 1.5 times 2 equals 11. And what this is telling me is, first, I look at the 3. Since that's my lower bound, I'm checking to see if I have any data points smaller than 3. Well, yes, I do. I have a value or a data point at 2. Then I look at 11. Since that's my upper bound, I ask myself, do I have any data values greater than 11? And that answer is no, which tells me I only have one outlier, and that outlier is at 2. So I would say because 2 hours of sleep is below my lower boundary of 3, 2 is an outlier. And this right here, this sentence is my answer. Now that I've determined an outlier, I found one, I need to go back to my box plot and I need to redo this and create a modified box plot. And what that means is, instead of having 2 as my minimum value, 2 is now an outlier and I have to redo that minimum value. So just drawing how I had before, so 1 through 9. Okay, at 2, instead of a dot, I'm going to do a star because that is now an outlier. My maximum on 8.5 stays the same. My Q3, my median, and my Q1 stay the same, but my minimum now changes. Okay, and I know what it changes to by going back up to my data here, and notice that no longer is 2 a part of my data, so my minimum value is going to be 4.5. So at 4.5, I am going to do a dot and label that minimum. So that means my box plot now is going to look like this. So notice that my left whisker is now a lot shorter, and I have my star over the 2, which indicates my outlier. So this would be my modified box plot. Okay. Last portion of the notes here is, now that we understand what a box plot is and we understand how to determine the shape of a distribution, we have to see that the shape of a box plot actually looks a little different when we're talking about the shape of a distribution. So for example, if we're trying to determine if the shape is symmetric and uniform, we know that the distribution looks like this. They're about all the same height. Well, looking at a box plot, that means that our box plot should be about the same on both sides. It should be symmetric. Okay, meaning if I was to divide this down the middle, I would have equal amount of data on both sides. Then what if I had symmetric bimodal? Well, symmetric bimodal, I know, is going to have two humps, and it's going to be symmetric down the middle, even on both sides. And for a box plot, what this looks like, it looks like I have a larger box than I do whiskers. Okay. However, notice that it is still symmetric down the middle. I just am seeing two humps of data. I have a big chunk of data here and a big chunk of data here. Okay. Next is symmetric unimodal. We will soon be calling this by its actual name, which is a bell-shaped curve. And when we're looking at a box plot here, what we're seeing is something a little similar to the symmetric uniform, okay? The median might not be exactly in the middle, but the whiskers and the box look proportionate to each other. And then we have the skewness, so left skewed and right skewed. So we know that left skewed means our data is on the right, and right skewed means our data is on the left. Okay, that also means that's how our boxes are going to look. So for left skewed, our data is going to be on the right with a longer whisker on the left. And then for right skewed, our data is going to be on the left with a longer whisker on the right.